Venus has always captivated humanity with its brilliance. As the brightest object in the night sky after the moon, this neighboring world seemed to promise something remarkable beneath its perpetual veil of clouds. Throughout much of human history, Venus represented beauty, mystery, and the tantalizing possibility of another Earth-like world spinning through space just next door. When the age of modern astronomy dawned, scientists turned their instruments skyward with growing excitement, eager to understand what secrets lay beneath those thick white clouds that completely obscured the planet's surface from view. The persistent cloud cover presented an immediate problem for early observers. While Mars revealed its reddish deserts and polar caps, and Jupiter displayed its swirling bands and storms, Venus remained frustratingly opaque. Telescopes of increasing power showed nothing more than a featureless disk of reflected sunlight. This very opacity, however, fueled speculation rather than dampening it. If clouds existed, then surely there must be water. Where there was water, perhaps there was life. These assumptions seemed perfectly reasonable given the limited understanding of planetary atmospheres in the late 19th and early 20th centuries. Scientists knew Venus was roughly the same size as Earth, with a diameter only about 650 kilometers smaller than our home planet. Its mass was similarly close to Earth's, at approximately 81.5% of our world's bulk. Such similarities suggested that Venus might possess comparable geological features, perhaps even oceans, forests, and breathable air. The planet's position in the solar system, though closer to the Sun than Earth, didn't initially raise major concerns. Yes, Venus received more solar radiation, but those reflective clouds might bounce much of that energy back into space, potentially creating a temperate world below. This thinking led to some wonderfully imaginative theories about what Venus might be like. In the early decades of the 20th century, respected astronomers proposed that Venus could be a younger, warmer version of Earth. Some suggested it might resemble our planet during the Carboniferous period, a time of lush swamp forests, giant ferns, and humid tropical conditions that covered much of Earth's landmass. The Swedish chemist and Nobel laureate Svante Arrhenius published a popular book in 1918 describing Venus as a warm, wet world with abundant vegetation. His scientific reputation lent considerable weight to these ideas, and many people imagined Venus as a steamy jungle planet, perhaps harboring exotic forms of life adapted to perpetual cloud cover and constant moisture. Others proposed that Venus might be entirely covered by a global ocean, with no land masses breaking the surface. This aquatic Venus theory suggested that the clouds were simply water vapor rising from warm seas below. Some variations of this hypothesis proposed that life could exist in these Venusian oceans, swimming in waters that might be somewhat warmer than Earth's tropical seas, but still potentially habitable. These weren't merely flights of fancy by science fiction writers, though such stories certainly proliferated. These were serious scientific hypotheses put forward by astronomers who were working with the limited observational data available at the time. A few voices offered more cautionary interpretations. Spectroscopic analysis of Venus's atmosphere began in the early 20th century, and these measurements detected significant amounts of carbon dioxide. By the 1930s, it became clear that carbon dioxide was a major constituent of the Venusian atmosphere, perhaps even the dominant gas. This finding troubled some scientists who understood that carbon dioxide could trap heat through what's known as the greenhouse effect. Still, without knowing the total atmospheric pressure or the exact composition of the clouds, it remained difficult to predict what conditions might truly exist at the surface. Radio astronomy emerged as a new tool for studying Venus in the 1950s. Unlike visible light, radio waves could penetrate the cloud layer, potentially revealing something about the conditions below. The results were startling and deeply puzzling. Measurements taken at various radio wavelengths suggested that Venus's surface might be quite hot, possibly several hundred degrees above the temperatures found on Earth. Some scientists proposed that Venus might have a hot surface with cool clouds above, while others argued that the radio emissions might come from the atmosphere itself rather than the surface, or perhaps from some kind of ionospheric phenomenon that didn't necessarily indicate scorching ground temperatures. The debate intensified throughout the 1950s. Some researchers clung to the hope that Venus might still harbor life, perhaps in cooler regions near the poles or at higher elevations if the planet had mountains. Others became increasingly convinced that Venus was likely hostile to life as we know it. The truth could only be determined through direct exploration, and that became possible with the advent of space technology. The Soviet Union launched the first spacecraft toward Venus in February 1961. Designated Venera 1, this probe was designed to fly past Venus and collect data about the planet's magnetic field, charged particles in space, and other properties that could be measured from a distance. The mission demonstrated the technical capability to send a spacecraft to another planet, though contact was lost with Venera 1 long before it reached its target. The probe passed within about 100,000 kilometers of Venus in May 1961, but it transmitted no data during the encounter because its radio had already failed. Despite this setback, the mission proved that interplanetary trajectories could be calculated and executed successfully. The space age had truly begun, and Venus became an obvious target for further exploration. The planet's relative proximity to Earth and its periodic close approaches every 19 months made it an attractive destination for early space missions. American and Soviet space planners both set their sights on being the first to successfully study Venus up close. The Americans attempted their first Venus mission in July 1962 with Mariner 1, but the rocket veered off course shortly after launch and had to be destroyed. Just a month later, however, Mariner 2 lifted off successfully and began its journey toward Venus. This spacecraft achieved a historic milestone when it flew past Venus in December 1962 at a distance of about 35,000 kilometers. Mariner 2 carried instruments to measure the temperature of Venus's clouds and surface by detecting infrared and microwave radiation. The data it returned shocked many scientists. Mariner 2's radiometer scans indicated that Venus was extraordinarily hot. The measurements suggested surface temperatures around 425 degrees Celsius, though with considerable uncertainty in the exact value. More disturbing still, the probe detected almost no difference in temperature between the day and night sides of the planet. This implied that Venus possessed a thick atmosphere capable of distributing heat globally, preventing any significant cooling even during the long Venusian night. The spacecraft also failed to detect any magnetic field, suggesting that Venus either rotated too slowly to generate one or lacked a liquid metallic core like Earth's. These findings created a scientific sensation, but also considerable controversy. Some researchers questioned the interpretation of the data, arguing that the measurements might reflect the temperature of the upper atmosphere or clouds rather than the actual surface. Others suggested that perhaps Venus had localized hotspots, possibly from volcanic activity, rather than being uniformly hot across the entire planet. The debate couldn't be settled by a single flyby mission. What was needed was a probe that could actually enter Venus's atmosphere and measure conditions directly as it descended toward the surface. The Soviet Union accepted this challenge with characteristic determination. Soviet scientists and engineers began designing atmospheric entry probes that could survive the descent through Venus's clouds and transmit data back to Earth. The technical difficulties were formidable. Nobody knew exactly what the probe would encounter. Would the atmospheric pressure at the surface be similar to Earth's or much higher? Would the temperature be hot enough to melt metals? How strong would the winds be? How dense was the atmosphere at different altitudes? All these unknowns had to be accounted for in the probe's design. Soviet engineers adopted a conservative approach, building their entry probes to be as robust as possible while keeping them light enough to launch on available rockets. The early Venera probes were spherical pressure vessels made of titanium and other heat-resistant materials, designed to protect delicate scientific instruments during entry and descent. Parachutes would slow the descent, giving the instruments time to collect measurements and transmit them back to a passing flyby module that would then relay the data to Earth. Venera 2 and Venera 3 launched toward Venus in November 1965. Both spacecraft consisted of a flyby bus and an atmospheric entry probe. The mission planners hoped that at least one would succeed in returning data from within Venus's atmosphere. Venera 2 was supposed to fly past Venus while releasing its lander, but the spacecraft suffered a failure and went silent before reaching the planet. Venera 3 fared somewhat better in that it maintained communication during most of its journey, but contact was lost just before arrival at Venus in March 1966. The entry probe crashed into the planet, becoming the first human-made object to reach another planet's surface, but it transmitted no data. These early failures were frustrating, but not entirely unexpected. Interplanetary missions were still in their infancy, and engineers were learning hard lessons about the reliability required for spacecraft that had to function perfectly after months in the harsh environment of space. The Soviet team analyzed the failures, redesigned problematic systems, and prepared the next generation of Venus probes. Venera 4 represented a significant advancement when it launched in June 1967. This mission featured improved communications, better thermal protection, and more sophisticated instruments to measure temperature, pressure, atmospheric composition, and other properties during descent. As Venera 4 approached Venus in October 1967, anticipation ran high. The Americans were also sending a spacecraft, Mariner 5, which would arrive at Venus just one day after Venera 4. The timing was coincidental, but it created an opportunity for comparing measurements from both missions. Venera 4's entry probe separated from its carrier spacecraft and plunged into Venus's atmosphere on October 18, 1967. The probe deployed its parachute and began transmitting data as it descended. For the first time, humanity received direct measurements from within another planet's atmosphere. The temperature readings climbed steadily as the probe sank deeper into the atmosphere. Pressure increased dramatically. The atmospheric composition measurements confirmed that carbon dioxide made up the vast majority of the atmosphere, more than 90% by volume. The probe transmitted data for 93 minutes as it descended. But then, the signal suddenly stopped. Soviet scientists initially announced that Venera 4 had reached the surface, but careful analysis of the data revealed a troubling inconsistency. The last pressure reading received from the probe was about 22 atmospheres, which was far higher than anyone had anticipated. However, Mariner 5 flew past Venus the next day and made measurements suggesting that the atmospheric pressure at the surface might be even higher, possibly 75 to 100 atmospheres. A heated scientific debate erupted. Had Venera 4 actually reached the surface and stopped transmitting for some other reason, or had the probe been crushed by unexpectedly high atmospheric pressure while still well above the ground? The telemetry data suggested the latter explanation. The temperature at the time of signal loss was around 280 degrees Celsius, which seemed too low if the probe had reached the surface, given the radio measurements indicating much higher surface temperatures. Eventually, scientists concluded that Venera 4 had been destroyed by atmospheric pressure at an altitude of roughly 25 kilometers above the surface. This realization was sobering. Venus was proving to be far more hostile than even pessimistic predictions had suggested. The atmospheric pressure was similar to what you'd experience nearly a kilometer deep in Earth's oceans. The temperature at the surface, based on extrapolation of Venera 4's measurements combined with radio astronomy data, might exceed 450 degrees Celsius, hot enough to melt lead. The thick carbon dioxide atmosphere was creating an extreme greenhouse effect, trapping solar heat so efficiently that Venus had become the hottest planet in the solar system, despite Mercury being closer to the Sun. The dream of a lush, life-bearing Venus was definitively dead. Instead of tropical swamps or warm oceans, Venus appeared to be a hellish pressure cooker, completely uninhabitable by any known form of life. The surface conditions would instantly crush and incinerate any Earth creature unfortunate enough to be transported there. This was one of the most profound revelations in the history of planetary science, fundamentally changing humanity's understanding of the solar system and the factors that make a planet habitable. Rather than becoming discouraged, Soviet scientists and engineers saw Venus's extreme conditions as a challenge to be overcome. If Venera 4 had been crushed at 22 atmospheres, then the next probe would be built to withstand 100 atmospheres or more. If the temperature reached 450 degrees Celsius or higher, the next probe would be designed with better heat shielding and more robust electronics. The Soviet space program had a tradition of learning from failures and pushing forward with improved designs. Venus would be conquered through persistence and clever engineering. The next pair of Venus probes, Venera 5 and Venera 6, launched in January 1969. These spacecraft incorporated some improvements based on lessons learned from Venera 4, but they weren't substantially more robust in terms of pressure tolerance. The engineers had hoped that Venera 4 might have been anomalously weak, or that the surface pressure might be at the lower end of the estimated range. Both Venera 5 and 6 successfully entered Venus's atmosphere in May 1969 and transmitted data during their descents. Both probes returned valuable measurements of atmospheric composition, temperature, and pressure at various altitudes, but both were also crushed before reaching the surface. Venera 5 transmitted for 53 minutes before succumbing to pressure at about 24 atmospheres. Venera 6 lasted 51 minutes and reached similar depths before being destroyed. These missions confirmed that Venus's surface pressure was indeed around 90 to 100 atmospheres, far beyond what the early probes had been designed to handle. The temperature profile was also better understood now. Venus's atmosphere was structured in layers, with relatively cool clouds high up and steadily increasing temperatures deeper down. The lower atmosphere was almost unimaginably hot and dense, more like a supercritical fluid than the gases humans were familiar with in Earth's atmosphere. Scientists now had enough data to begin understanding Venus's greenhouse effect in detail. The thick atmosphere trapped heat through multiple mechanisms. Carbon dioxide itself absorbs infrared radiation, preventing heat from escaping back into space. But the clouds also played a role. Analysis suggested these weren't water clouds like those on Earth, but rather clouds composed of sulfuric acid droplets. These clouds reflected much of the incoming sunlight, which was actually the only thing preventing Venus from being even hotter than it was. Below the clouds, however, the dense atmosphere acted like an insulating blanket, trapping every bit of heat that did make it to the surface. The Soviet team went back to the drawing board. Building a probe capable of surviving long enough to reach Venus's surface and transmit data would require a complete redesign. The pressure vessel needed to be much stronger. The heat shielding had to be more effective. The electronics had to function at temperatures that would normally destroy standard components. Every system had to be re-engineered with Venus's brutal environment in mind. While the engineers worked on their redesigns, the scientific community continued refining their understanding of Venus's atmosphere through Earth-based observations and data from flyby missions. Every new piece of information made it clearer just how wrong the early assumptions had been. The planet that had once been imagined as a tropical paradise was revealing itself to be one of the most hostile places in the solar system. The atmospheric composition turned out to be another shock. Carbon dioxide made up more than 96% of the atmosphere. This wasn't just a thick blanket of air. It was a dense ocean of gas, creating a greenhouse effect so powerful that it had turned Venus into a planetary furnace. The remaining small percentage consisted of nitrogen and trace amounts of other gases, including sulfuric acid clouds that shrouded the entire planet. Those beautiful, mysterious clouds that had captivated astronomers for centuries weren't water vapor at all. They were concentrated acid droplets that would corrode most metals on contact. Understanding the chemical makeup of the atmosphere added another layer of complexity to the probe design. Materials that might withstand the pressure and heat could still be eaten away by the corrosive atmosphere. The Soviet engineers had to find substances that could resist all three threats simultaneously. This meant testing materials under conditions that mimicked Venus as closely as possible, creating special chambers that could replicate the crushing pressure, searing heat, and corrosive chemistry all at once. The electronics posed perhaps the most difficult challenge. Semiconductors, the foundation of all electronic equipment, had fundamental limitations when it came to temperature. Silicon-based transistors simply stopped working properly above certain temperatures. The heat caused electrons to move erratically, making circuits unreliable or completely non-functional. The standard electronics would fail within minutes on Venus's surface. The team needed solutions that could function at temperatures hot enough to melt lead. One approach involved developing special cooling systems for the electronics. These systems would essentially create a small, protected environment inside the probe where the electronics could operate at manageable temperatures. But cooling systems required energy, and energy meant batteries or other power sources that also had to survive the Venus environment. The entire design became a complex puzzle where every piece affected every other piece. Another strategy focused on creating electronics that could actually function at high temperatures. This meant going back to older, more robust technologies in some cases. Vacuum tubes, those bulky glass cylinders that had been largely replaced by transistors in most applications, could actually operate at much higher temperatures than their solid-state counterparts. Soviet engineers began incorporating these seemingly obsolete components into their probe designs. They also experimented with new semiconductor materials that had higher temperature tolerances than standard silicon. The communication system faced its own set of challenges. The probe needed to transmit data back to Earth, which meant sending radio signals through Venus's thick atmosphere. The dense layers of gas and clouds would interfere with these signals, potentially distorting or blocking them entirely. The transmitter had to be powerful enough to punch through the atmospheric interference while being compact enough to fit inside the probe and efficient enough to operate on limited battery power. As the Venera program continued, each mission built upon the lessons of previous attempts. Venera 4, launched in June 1967, represented a major step forward in probe design. The spacecraft carried a much more robust descent capsule with improved heat shielding and stronger construction. The Soviet team was confident this time. They'd learned from their failures. They'd strengthened every weak point they could identify. Venera 4 reached Venus in October 1967 and released its descent capsule into the atmosphere. The probe began transmitting data almost immediately, sending back information about temperature, pressure, and atmospheric composition as it descended. The readings were remarkable. The temperature rose steadily as the probe fell deeper into the atmosphere. The pressure increased relentlessly. The data streamed back to Earth, giving scientists their first detailed profile of Venus's atmospheric structure. Then, after 94 minutes of descent, the transmission stopped. The probe had gone silent at an altitude the Soviet team calculated to be about 15 miles above the surface. They'd made it much deeper than any previous attempt, but they still hadn't reached the ground. The conditions had simply overwhelmed the spacecraft before it could complete its mission. The frustration must have been immense, but so was the determination. The data from Venera 4 provided crucial information about just how extreme the lower atmosphere really was. Scientists calculated that the pressure at the surface had to be far greater than anyone had previously estimated. Some new models suggested pressures approaching 100 times that of Earth's atmosphere at sea level. The temperature estimates also climbed higher, with surface temperatures now thought to exceed 800 degrees Fahrenheit. These weren't just numbers on a page. They represented a complete re-evaluation of what it would take to land on Venus. The Soviet engineers realized they'd been designing their probes to survive conditions that were still far less severe than what actually existed on the surface. The pressure vessels needed to be even stronger. The heat protection had to be even more effective. The mission timelines had to account for longer descent times and more prolonged exposure to harsh conditions. The United States, meanwhile, was pursuing its own Venus exploration through the Mariner program. Mariner 5 flew past Venus just one day after Venera 4 arrived, conducting its own atmospheric studies during the flyby. The American probe's radio occultation experiments, which analyzed how Venus's atmosphere affected radio signals passing through it, provided independent measurements of atmospheric density and pressure. The data from Mariner 5 confirmed what Venera 4 had suggested. The surface pressure was indeed far higher than earlier estimates. This moment represented an interesting intersection of Cold War space competition and scientific cooperation. Despite the political tensions between the Soviet Union and the United States, scientists on both sides shared data and compared results. The Venus exploration became one area where the pursuit of knowledge occasionally transcended political divisions. American scientists acknowledged the pioneering work of the Venera program, while Soviet researchers incorporated findings from American missions into their own planning. The Venera team pressed forward with increasingly robust designs. Venera 5 and Venera 6, launched in early 1969, carried improved pressure vessels and enhanced thermal protection. Both probes successfully entered Venus's atmosphere and transmitted data during their descent. Both, however, still failed to reach the surface. They transmitted for slightly longer than Venera 4, but ultimately succumbed to the crushing pressure at altitudes estimated to be around 12 miles above the ground. Each failure, though disappointing, provided more data points. The engineers could see exactly where and how their designs were failing. They could measure how long different components lasted under real Venus conditions rather than simulated ones. This empirical evidence was invaluable for refining their approach. The probes were essentially sacrificial experiments, pushing the boundaries of what was possible and revealing the next set of obstacles to overcome. The pressure vessel design underwent radical changes. The spherical shape, which distributed pressure evenly across the surface, was retained as the most efficient geometry. But the walls of the sphere grew thicker. The materials became stronger. The seals and joints received special attention, as any weak point could become a catastrophic failure point under such extreme pressure. The engineers tested different titanium alloys, looking for the optimal combination of strength, weight, and durability. Thermal protection evolved into a multi-layer system. The outer heat shield, designed to handle the intense heat of atmospheric entry, was followed by layers of insulation that would slow the transfer of heat to the interior. Some designs incorporated phase change materials that would absorb heat by melting or vaporizing, buying precious time for the electronics inside. The cooling systems for the electronics became more sophisticated, using compressed gases or other techniques to maintain a survivable temperature inside the instrument compartment for as long as possible. The timeline for a successful landing kept getting pushed back as each mission revealed new challenges. But the Soviet program maintained its momentum. Resources continued to flow into the Venera program. Teams of engineers and scientists worked through the problems methodically. There was a sense that success was possible, that with enough refinement and improvement, they could build a probe that would survive long enough to reach the surface and send back data. Venera 7, launched in August 1970, represented the culmination of everything the program had learned. The pressure vessel was the strongest yet, designed to withstand pressures up to 180 atmospheres. The thermal protection system incorporated all the latest improvements. The electronics were protected by an enhanced cooling system designed to maintain survivable temperatures for an extended period. The transmitter was more powerful. The entire spacecraft was engineered with a single goal in mind: to reach the surface of Venus and transmit data back to Earth. The descent on December 15, 1970, was tense. Engineers and scientists at the tracking station monitored the signals as the probe plunged into the atmosphere. The data stream showed the now familiar pattern of rising temperature and increasing pressure. The minutes ticked by. The probe passed the altitude where previous missions had failed. It kept descending. The signals continued. Then, after 35 minutes of descent, the signal weakened significantly but didn't stop completely. For 23 minutes more, a faint signal continued to transmit from the surface of Venus. The probe had made it. Venera 7 had become the first spacecraft from Earth to land on another planet and successfully transmit data from the surface. The signal was weak, the data limited, but it was real. Human technology had touched down on a world so hostile that reaching it had required years of failure, learning, and innovation. The surface temperature reading was confirmed at around 475 degrees Celsius, or about 887 degrees Fahrenheit. The pressure was measured at 92 atmospheres. These numbers represented ground truth, actual measurements from the surface rather than estimates or calculations. Venus was officially confirmed as the hottest planet in the solar system, despite being farther from the Sun than Mercury. The greenhouse effect created by the dense carbon dioxide atmosphere was so powerful that it trapped heat far more effectively than Mercury's thin atmosphere could. The achievement of Venera 7 was celebrated, but also immediately analyzed for lessons about what had worked and what could be improved. The weak signal suggested that something had partially failed, possibly damage during landing or degradation of the antenna system. The limited data transmission meant there was still room for improvement. A successful landing was just the first step. The next goal was to land and operate long enough to gather comprehensive scientific data. The Soviet engineers went back to work on refinements. Venera 8, launched in March 1972, carried improvements based on the Venera 7 experience. The landing system was redesigned to reduce impact forces. The communication system was enhanced to provide a stronger signal. The instrument package was expanded to gather more types of data. Venera 8 landed successfully on July 22, 1972, and transmitted data for 50 minutes before the extreme conditions finally disabled it. The stronger signal and longer operational life allowed scientists to gather much more information than Venera 7 had provided. The probe measured light levels on the surface, confirming that despite the thick cloud cover, enough sunlight penetrated to the surface to make photography theoretically possible. This finding would shape the design of future missions. The amount of data coming back from these successful landings began to paint a detailed picture of Venus's surface environment. The chemical analysis instruments confirmed that the surface rocks were similar to basaltic formations found on Earth, suggesting volcanic origins. This wasn't surprising, as Venus showed evidence of extensive volcanic activity in its past. The atmospheric composition measurements at the surface matched what had been detected at higher altitudes, showing a consistent ocean of carbon dioxide with traces of other gases. Temperature measurements taken at different locations on the surface showed remarkable consistency. Whether landing on the day side or night side, in equatorial regions or higher latitudes, the surface temperature remained around 460 to 480 degrees Celsius. The thick atmosphere distributed heat so effectively around the planet that there were virtually no temperature variations. This was radically different from Earth, where temperature varies dramatically with location and time of day. On Venus, the greenhouse effect had created a planetary oven with uniform heat distribution. The scientific community worldwide was now paying close attention to Venus exploration. The data coming from the Venera missions was revolutionizing planetary science. Before these missions, planets were largely understood through observation and theory. Now, for the first time, scientists had direct measurements from the surface of another world. The findings about atmospheric pressure, temperature, and composition informed models of planetary atmospheres throughout the solar system. Understanding Venus's runaway greenhouse effect provided insights into climate dynamics that were relevant to Earth as well. The question of why Venus turned out so differently from Earth became a major focus of planetary science research. Both planets were similar in size and composition. They'd formed from the same region of the early solar system, yet Earth had developed a temperate climate with liquid water oceans and eventually life, while Venus had become a hellish world with surface conditions incompatible with any known form of life. Understanding this divergence could help scientists understand the factors that make a planet habitable or uninhabitable. The leading theory involved Venus's proximity to the Sun. Being slightly closer to the Sun meant Venus received more solar radiation than Earth. In the early solar system, this extra heat might have prevented water vapor from condensing into liquid oceans. Instead, the water remained in the atmosphere as vapor, which is itself a greenhouse gas. This created a feedback loop. The water vapor trapped more heat, which caused more water to remain in vapor form, which trapped even more heat. Over time, the increasing temperature caused other greenhouse gases like carbon dioxide, which might have been locked in rocks, to be released into the atmosphere, intensifying the effect even further. On Earth, by contrast, water condensed into oceans early in the planet's history. These oceans absorbed much of the carbon dioxide from the atmosphere. Some of this carbon dioxide was eventually locked away in carbonate rocks through geological processes. The presence of liquid water also allowed life to develop, and living organisms further modified Earth's atmosphere over billions of years. Earth's climate system included numerous feedback mechanisms that kept temperatures relatively stable within a range suitable for liquid water. Understanding that Venus might have once had a different climate, possibly even with liquid water on its surface before the runaway greenhouse effect took hold, raised fascinating questions. Could Venus have harbored life billions of years ago before conditions became too extreme? The surface conditions were now so severe that any evidence of ancient life would have been destroyed, but the question remained tantalizing. It also served as a stark reminder of how planetary climates could change dramatically over geological timescales. The success of Venera 7 and 8 set the stage for even more ambitious missions. If the Soviet engineers could land probes that survived for nearly an hour in Venus's extreme environment, could they design probes that would do more than just measure atmospheric conditions? Could they actually photograph the surface? Could they analyze rock samples? Could they deploy instruments that would operate for extended periods? Photography presented unique challenges. Cameras had to be protected from the heat and pressure just like any other electronic equipment. But they also needed a clear view of the surface, which meant having windows or openings in the pressure vessel. Any window was a potential weak point where the seal might fail. The intense heat could distort or crack glass or other transparent materials. The optical systems had to function in conditions that would damage standard cameras within seconds. The Soviet team developed special camera systems designed specifically for Venus conditions. The cameras used wide-angle lenses to capture as much of the surrounding terrain as possible in a single image. The viewing ports were constructed from materials that could withstand the pressure and heat. The camera systems were designed to take images quickly after landing, maximizing the chance of getting usable pictures before the extreme conditions degraded the equipment. Venera 9 and 10, launched in 1975, were the missions designed to return the first images from the surface of another planet. These probes were substantially more complex than their predecessors. Each consisted of an orbiter and a lander. The orbiter would remain in orbit around Venus to serve as a communications relay, ensuring that the lander's signals could be received even if the direct path to Earth was blocked. This dual spacecraft approach significantly increased the chances of mission success. The landers carried the camera systems along with improved versions of the instruments from previous missions. They also incorporated new drilling systems designed to collect and analyze soil samples from just beneath the surface. Every aspect of the mission had been planned to maximize scientific return during the limited time the landers would survive on the surface. Venera 9 touched down on October 22, 1975, on a rocky slope near Beta Regio, a highland region on Venus. The landing system worked as designed, bringing the probe to rest in an upright position. The camera system activated and began scanning the landscape. For the first time, human beings would see what the surface of Venus actually looked like. The images that came back were grainy and monochrome, limited by the technology of the time and the conditions under which they were captured. But they were revolutionary. The pictures showed a rocky landscape strewn with sharp-edged stones. The rocks were angular, suggesting relatively young geological features that hadn't been worn smooth by weathering. The lighting was diffuse, filtered through the thick cloud layers above, but bright enough to clearly illuminate the surface. It looked, in some ways, surprisingly Earth-like, even though the conditions were anything but. Venera 9 transmitted data for 53 minutes before the harsh environment finally shut it down. 3 days later, Venera 10 landed in a different region and sent back its own set of images. This second landing site appeared flatter, with older, more weathered rocks. The differences between the two sites suggested that Venus had varied terrain features despite the uniform environmental conditions. The images from Venera 9 and 10 captured public imagination worldwide. These weren't artists' conceptions or theoretical models. They were real photographs of an alien world. The fact that they'd been obtained from a place where the temperature was hot enough to glow red, under pressure that would instantly crush an unprotected human, made the achievement all the more remarkable. The technology and determination required to capture these images represented a triumph of engineering and scientific ambition. Now, the achievement didn't go unnoticed by the scientific community. NASA officials acknowledged the extraordinary success of the Soviet missions, though their own focus remained primarily on Mars. The American program had achieved spectacular successes with Mars orbiters and landers, capturing stunning images of red deserts and canyon systems. But Venus belonged to the Soviets, at least for the moment. They'd cracked a problem that had stumped everyone, and they'd done it through systematic trial and error, learning from each failure and applying those lessons to subsequent attempts. With the photographs in hand, scientists could now correlate what they saw with the instrument readings. The dark rocks visible in the images turned out to be basaltic in composition, similar to volcanic rocks found on Earth. The flat, layered appearance suggested sedimentary processes, though not necessarily water-based ones. The lighting conditions, once mysterious, now made sense. The thick atmosphere scattered light so effectively that shadows became soft and diffuse, creating what photographers would recognize as the ultimate overcast day. No harsh contrasts, no sharp edges, just a strange twilight illumination that came from everywhere and nowhere at once. The success of Venera 9 and 10 energized the Soviet program for additional missions. Engineers began planning more sophisticated landers with extended capabilities. The basic pressure vessel design had proven itself, but now they could focus on improving the cameras, adding new instruments, and extending operational lifetimes. Perhaps future landers could survive for hours instead of minutes. Perhaps they could even include mobility, though the extreme conditions made any kind of rover mechanism extraordinarily challenging. Venera 11 and 12 followed in 1978, each carrying improved instrumentation packages. The designers equipped these probes with color cameras, hoping to reveal what Venus actually looked like beyond the black and white imagery. They also included more sophisticated atmospheric analysis equipment and instruments designed to search for lightning and seismic activity. The mission successfully reached the surface and transmitted data, though frustratingly, Both experienced camera failures. The mechanical covers designed to protect the camera lenses during descent failed to eject properly on both landers. After all the effort to reach the surface intact, after all the engineering invested in creating cameras that could function in such extreme heat, a relatively simple mechanical system failed on both spacecraft. The irony wasn't lost on the mission teams. Despite the camera failures, Venera 11 and 12 did collect valuable atmospheric data. They detected what appeared to be electrical discharges in the atmosphere, providing evidence for lightning activity within the Venusian clouds. The frequency and intensity of these discharges surprised researchers. Venus apparently experienced lightning storms of considerable power, adding another layer of drama to an already violent environment. The landers also sampled the atmosphere at different altitudes during descent, building a more complete profile of temperature, pressure, and composition from the cloud tops down to the surface. The setback with the cameras didn't diminish the Soviet commitment to Venus exploration. If anything, it reinforced the lesson that success required persistence and redundancy. Engineers redesigned the camera protection systems for subsequent missions, adding multiple failure safeguards. They also began developing backup imaging systems, recognizing that relying on a single camera design introduced unnecessary risk. Venera 13 and 14 launched in 1981, representing the next generation of Soviet Venus landers. These spacecraft carried improved cameras with the mechanical problems from Venera 11 and 12 corrected. They also featured drill systems designed to obtain soil samples for analysis, extending the scientific capabilities beyond passive observation. The engineers had pushed the operational lifetime goals as well, designing systems they hoped might function for an hour or more on the surface. Both landers succeeded brilliantly. Venera 13 transmitted color photographs from the surface, revealing for the first time the true appearance of Venus. The images showed an orange-tinted landscape under a thick, orange sky. The color came from the way the massive atmosphere filtered sunlight, removing blue wavelengths and allowing the longer red and orange wavelengths to predominate. The rocks visible in the images displayed layered structures and varied compositions, some appearing dark and volcanic, others lighter and possibly sedimentary. The drill successfully penetrated the surface and delivered samples to the onboard analytical laboratory, which identified the soil as containing materials similar to terrestrial basalts with some unusual chemical variations. Venera 13 operated for 127 minutes on the surface, far exceeding the design specifications. The temperature during this period hovered around 457 degrees Celsius, and the pressure measured approximately 89 atmospheres. That the spacecraft continued functioning under these conditions for more than 2 hours represented an extraordinary engineering achievement. Every system, every component, every seal and bearing had been designed and tested to withstand an environment that no human-made device had previously survived for such duration. Venera 14 touched down successfully as well, transmitting color images and successfully drilling into the surface. The images revealed a slightly different terrain from the Venera 13 landing site, with more abundant flat plate-like rocks. The drill obtained soil samples that showed different chemical compositions, suggesting regional variations in surface materials. Venera 14 operated for 57 minutes before succumbing to the heat and pressure, still an impressive performance though shorter than its twins record. One aspect of the Venera 13 and 14 missions that didn't receive as much public attention but fascinated scientists involved the acoustic experiments. Both landers carried microphones designed to record sounds from the Venusian surface. These weren't sophisticated devices, just simple microphones protected as well as possible from the extreme conditions. But they succeeded in capturing audio from another planet's surface for the first time in history. The recordings revealed a range of sounds, including the creaks and groans of the lander's structures adjusting to the extreme environment, the rumble of what might have been distant thunder or seismic activity, and the rush of wind across the microphone. The thick atmosphere conducted sound well, but in unfamiliar ways. The acoustic environment of Venus proved to be as alien as its visual appearance. The color photographs from these missions answered questions that had puzzled scientists since the first images arrived from Venera 9. Why did the surface appear so uniform in the black and white images? The answer became clear in color. The orange atmospheric filtering and the thick haze created a visual environment where color contrast became muted and objects at any distance faded into an orange fog. The lighting remained diffuse and directionless, creating that shadowless illumination that made depth perception difficult. Standing on Venus, if such a thing were possible, would feel like existing inside an orange cloud with the ground as the only solid reference point. The success of Venera 13 and 14 marked the high point of direct Soviet Venus surface exploration, at least in terms of public impact and scientific return. The images captured by these missions appeared in textbooks, documentaries, and popular science publications worldwide. They represented the closest humans had come to experiencing Venus firsthand, at least visually and sensorially. The color photographs especially resonated with public imagination because they removed the last layer of abstraction. Black and white images could be imagined in any color scheme, but seeing the actual orange tint, the hazy sky, the textured rocks, made Venus real in a way previous data hadn't quite achieved. Soviet engineers continued pushing forward with additional missions. Venera 15 and 16, launched in 1983, took a different approach by remaining in orbit rather than attempting surface landings. These spacecraft carried radar mapping equipment designed to peer through the thick clouds and create detailed topographic maps of the Venusian surface. The missions successfully mapped the northern hemisphere with unprecedented detail, revealing vast highland regions, volcanic features, and mysterious geological structures unlike anything seen on Earth or other planets. The radar mapping missions proved that Venus exploration didn't require surface landings to generate valuable science. From orbit, instruments could survey vast areas and build up comprehensive datasets about surface features, atmospheric dynamics, and global weather patterns. The orbital perspective complemented the ground truth provided by the landers, creating a more complete picture of Venus as a complex, dynamic world. Vega 1 and 2, launched in 1984, represented another evolution in Soviet Venus exploration strategy. These missions combined Venus flybys with balloons deployed into the Venusian atmosphere. The balloons floated at altitudes where the temperature and pressure, while still extreme by Earth standards, permitted more extended operation than surface landers could achieve. The balloons drifted with the winds for nearly 2 Earth days, transmitting data about cloud chemistry, wind speeds, atmospheric structure, and other parameters that help scientists understand the planet's meteorology. The balloon experiments revealed a more dynamic atmosphere than static measurements had suggested, with powerful wind currents, turbulent mixing, and complex circulation patterns. While the balloon missions proceeded, engineers also prepared additional surface landers. Venera lost some of its political importance as Soviet attention shifted toward other priorities, but the scientific community remained committed to extracting more knowledge from Earth's hellish twin. The engineering expertise developed through the Venera program represented a valuable resource, and scientists had no shortage of questions that required additional data to answer. By the mid-1980s, the Soviet Union had achieved something remarkable in planetary exploration. They developed the capability to reliably land spacecraft on Venus and operate them long enough to collect meaningful scientific data. They'd photographed the surface in black and white and color. They'd analyzed soil samples, measured atmospheric conditions from the cloud tops to the ground, recorded sounds, detected lightning, and mapped the surface from orbit. The accumulated knowledge transformed Venus from a mysterious world shrouded in clouds to a place where scientists understood the basic parameters, even if many details remained unclear. The question of why Venus became so dramatically different from Earth gained importance as more data accumulated. Both planets formed from similar materials at similar distances from the Sun. Both had roughly the same size and mass. Both probably started with water oceans and potentially habitable conditions. Yet Venus ended up as a hell world, while Earth developed an environment where life flourished. Understanding this divergence became critical, not just for planetary science, but for understanding Earth's own climate system. Scientists developed theories about what they called runaway greenhouse effects. The basic mechanism seemed straightforward in outline, though devilishly complex in detail. Early in Venus's history, the planet probably received slightly more solar radiation than Earth because of its closer proximity to the Sun. This extra heat evaporated more water into the atmosphere. Water vapor is itself a greenhouse gas, trapping heat and causing further warming. The warming evaporated more water, which trapped more heat, creating a feedback loop. Eventually, the oceans boiled away entirely, their water molecules broken apart by ultraviolet radiation in the upper atmosphere. The hydrogen escaped to space, while the oxygen combined with surface rocks. Without water to lock up carbon dioxide in carbonates and biological cycles, Venus's carbon dioxide accumulated in the atmosphere. Volcanic outgassing added more. The growing concentration of carbon dioxide intensified the greenhouse effect, driving temperatures higher. Eventually, the planet reached the state observed today, with a dense carbon dioxide atmosphere, creating surface temperatures hot enough to melt lead. The process appeared inevitable once initiated, a one-way transformation from potentially habitable world to scorched wasteland. The implications for Earth were sobering. While Earth wasn't about to become Venus anytime soon, the basic physics of greenhouse effects applied to both planets. Adding carbon dioxide to Earth's atmosphere would warm the planet. The question wasn't whether this would happen, but how much warming would occur and how quickly. Venus served as a cautionary example of how a planet's climate could spiral out of control under certain conditions. The thick atmosphere that crushed Soviet landers and the surface temperatures that melted their components represented the end state of processes that, in milder form, influenced Earth's own climate. Scientists also puzzled over Venus's lack of a magnetic field. Earth's magnetic field, generated by convection currents in its molten iron core, shields the planet from solar wind and cosmic radiation. Venus appeared to lack this protection, at least according to measurements from various missions. The reasons remained unclear. Perhaps Venus's core had solidified, stopping the convection currents. Perhaps the planet's slow rotation, taking 243 Earth days to complete one turn, prevented the generation of a strong magnetic field. Whatever the cause, the absence of magnetic protection meant that solar wind directly interacted with Venus's upper atmosphere, creating complex electrical phenomena and contributing to the loss of water vapor to space over billions of years. The atmospheric superrotation also demanded explanation. Venus rotated incredibly slowly on its axis, yet its atmosphere whipped around the planet in just 4 Earth days at cloud-top altitudes. Something drove these powerful winds, but the energy source and mechanisms remain topics of active research. Computer models struggled to reproduce the observed circulation patterns. Understanding why Venus's atmosphere behaves so differently from Earth's became important for developing more general theories of planetary atmospheres. As the 1980s progressed, economic and political pressures within the Soviet Union began affecting space program funding. The Venera program had achieved its major objectives. Further missions would certainly generate valuable science, but they required resources that increasingly competed with other priorities. The last dedicated Venera surface mission launched in 1985, continuing the tradition of pushing engineering boundaries while collecting scientific data about surface composition and atmospheric conditions. Western attention to Venus exploration had waxed and waned over the decades. NASA sent several missions to Venus, including the successful Pioneer Venus Orbiter and Multiprobe mission in 1978, which greatly expanded understanding of the planet's atmosphere and magnetic environment. But American planetary science efforts concentrated more heavily on Mars, which seemed more promising for astrobiology research and potential future human exploration. The extreme conditions on Venus made it less attractive for mission planners working within NASA's budget constraints. The Magellan mission, launched by NASA in 1989, represented a major Western contribution to Venus science. The spacecraft carried sophisticated radar mapping equipment that created detailed global maps of the Venusian surface. Operating from 1990 to 1994, Magellan revealed a world dominated by volcanic features, with relatively few impact craters suggesting a geologically young surface. The radar images showed vast lava plains, enormous shield volcanoes, peculiar circular features called coronae, and complex tectonic structures. Venus clearly remained geologically active, or at least had been active in the recent geological past. The Magellan data, combined with information from Soviet missions, created a comprehensive picture of Venus as a world shaped by volcanic processes and unusual tectonics. Unlike Earth, Venus showed no evidence of plate tectonics, the system of moving crustal plates that drives much of Earth's geological activity. Instead, Venus appeared to resurface itself periodically through massive volcanic episodes that covered large portions of the planet with fresh lava. The lack of plate tectonics might relate to the planet's extreme heat, which could make the crust more ductile and less able to form rigid plates. By the mid-1990s, Venus science had reached a mature phase. The basic parameters were well established. The major surface features had been mapped. The atmospheric structure and composition were understood in broad terms. Scientists could explain many of Venus's characteristics, even if important details remained unclear. But without new missions generating fresh data, progress slowed. Computer models became more sophisticated, and researchers reanalyzed existing data in new ways, but breakthrough discoveries became less frequent. The early misconceptions about Venus, those optimistic visions of tropical rainforests and alien civilizations, seemed almost quaint from the perspective of accumulated knowledge. Scientists in the early 20th century had worked with the limited tools and data available to them. They'd made reasonable inferences based on what they could observe. The fact that those inferences proved wildly incorrect didn't diminish the intellectual rigor they brought to the problem. Science progresses through exactly this process, making observations, forming hypotheses, testing predictions, and revising understanding when new evidence arrives. What made Venus exploration compelling wasn't just the scientific results, though those were certainly valuable. The story also illustrated how persistence and ingenuity could overcome extraordinary technical challenges. The Soviet engineers who designed the Venera landers worked within constraints that would have deterred less determined efforts. They faced a target environment that seemed almost deliberately designed to destroy spacecraft. Temperature and pressure alone posed enormous challenges, but the corrosive atmosphere, the cloud chemistry, and the unknown surface conditions added layers of additional difficulty. Each mission taught lessons that informed subsequent attempts. The early failures, while disappointing, provided essential information about what wouldn't work. The first successes showed what approaches had promise. The incremental improvements in performance, from surviving seconds to surviving minutes to surviving hours, demonstrated how systematic engineering development could push the boundaries of what seemed possible. The photographs transmitted from the surface represented not just images of an alien landscape, but proof that human technology could function in one of the solar system's most hostile environments. The contrast between expectations and reality made the Venus story particularly striking. Scientists hoped to find a world that might harbor life, or at least conditions amenable to it. Instead, they discovered a hell world that challenged the limits of engineering. But rather than abandon the effort, Soviet scientists and engineers persisted. They developed new technologies, refined their designs, and ultimately succeeded in placing functional spacecraft on the surface and obtaining data that transformed scientific understanding. Modern proposals for Venus exploration build on foundations laid by those early missions. Scientists now discuss concepts like floating research stations in the temperate cloud layers, where temperatures and pressures are relatively benign. Others propose advanced landers that could operate for weeks or months rather than hours by using novel cooling systems or high-temperature electronics. Some researchers even suggest that Venus's clouds might harbor microbial life in the acidic droplets where temperatures permit liquid chemistry. Finding evidence for such life would revolutionize astrobiology, though the challenges of confirming its existence in such an environment appear daunting. The question of whether Venus was once habitable, perhaps billions of years ago before the runaway greenhouse destroyed any oceans, drives some research proposals. If Venus did have liquid water oceans early in its history, then life might have emerged just as it did on early Earth. Even if that life is long extinct, traces might remain in protected locations or in the geochemical record. The searching for such evidence would require sophisticated missions capable of detailed geological analysis, probably including sample return capabilities. Climate scientists increasingly view Venus as a natural laboratory for studying extreme greenhouse effects. While Earth will never become Venus, understanding the mechanisms that drove Venus's climate transformation helps calibrate models of how Earth's climate might respond to various forcings. The physics of heat transport, cloud formation, and atmospheric circulation apply to both planets, even though the specific conditions differ dramatically. Venus serves as a test case for climate models, a place where predictions can be checked against observations of an actual planetary atmosphere under extreme conditions. The engineering legacy of the Venera program extends beyond Venus exploration. The techniques developed for surviving extreme heat and pressure find applications in other hostile environments, both in space and on Earth. Deep ocean submersibles face pressure challenges comparable to Venus's surface, though not the temperature extremes. Electronics for high-temperature industrial processes benefit from research into heat-resistant components. Materials science advanced through the need to find substances that could maintain structural integrity and electrical properties under Venus-like conditions. Looking back at the progression of Venus exploration, from the early romantic speculations through the shocking discoveries of reality to the eventual successful missions, provides perspective on how scientific understanding develops. Scientists didn't fail when their initial theories proved wrong. They succeeded by being willing to revise those theories when evidence demanded it. The process took time, required patience, and demanded resources, but it ultimately produced reliable knowledge about a neighboring world. The human dimension of Venus exploration shouldn't be overlooked. Behind every mission were teams of engineers, scientists, technicians, and support staff who dedicated years of their lives to making those missions succeed. They worked through failures and frustrations, celebrated successes, and contributed to a collective effort that expanded human knowledge. The Soviet engineers who designed the Venera landers never visited Venus themselves, but they sent emissaries of human curiosity and technological capability. The photographs transmitted from the surface, those grainy images showing rocks and sky under impossible conditions, represent the visible legacy of thousands of person-years of effort. Venus continues to hold mysteries that future missions might unravel. The possibility of current volcanic activity remains uncertain. The details of atmospheric chemistry and circulation need more complete investigation. The geological history that shaped the surface features visible in radar maps requires better understanding. Questions about past habitability and potential microbial life in the clouds demand answers. Each question offers motivation for new missions, though the extreme conditions ensure that Venus exploration will never be easy. The story of Venus exploration illustrates how science transforms ignorance into knowledge through careful observation and creative problem-solving. It shows how technological development enables new discoveries and how each discovery raises new questions. It demonstrates that the universe contains environments alien to human experience, places where our intuitions fail and our tools barely function. Yet human curiosity and ingenuity found ways to reach even those places, to survive long enough in those alien conditions to gather data and transmit it across millions of miles back to Earth. The transformation of Venus from cloud-shrouded mystery to understood, if still fascinating world, took decades and required contributions from scientists and engineers across multiple nations. The Soviet Venera program deserves special recognition for achieving what many considered impossible, successfully landing functional spacecraft on Venus's surface and obtaining direct observations and measurements. Those achievements, born from persistence in the face of repeated failures, represent humanity's capability to overcome extraordinary challenges when motivated by the desire to understand our universe. Venus remains Earth's nearest planetary neighbor, and in some ways, its most alien. The planet that early scientists imagined might harbor life instead became an example of how planetary evolution can follow dramatically different paths from seemingly similar starting conditions. The lessons learned from studying Venus inform our understanding of climate, geology, atmospheric science, and planetary evolution. The engineering solutions developed to explore Venus expand the boundaries of what human technology can accomplish. The photographs transmitted from the surface remind us that the universe contains wonders we can observe and study, even if we cannot yet visit them in person. The narrative of Venus exploration, from hopeful speculation through harsh discovery to technological triumph, captures essential elements of the scientific endeavor. We begin with questions and imagination. We develop tools and methods to test our ideas. We face setbacks and failures, but persist. We eventually achieve understanding, though often finding that reality differs dramatically from our expectations. Throughout the process, human ingenuity and determination drive progress, pushing against the limits of what seems possible. Venus, that bright beacon in our sky, became a destination for human-built machines and a source of knowledge that enriched our understanding of planets, atmospheres, and our own world's place in the solar system. The engineers and scientists who made Venus exploration possible demonstrated that no environment is too hostile for human curiosity to investigate, given sufficient creativity and resolve.